SwayamPrabha. Digital India. Educated India.
Hello. Now we will discuss one other small concept, but a very profound concept in calculus of variations called general variation that leads to a number of interesting things such as what we call transversality conditions, broken extremals. By broken, what we mean is actually not made in two pieces, but something that has a kink, right. Instead of having a smooth curve, there will be a kink such as this, that is called broken extremal. As if you have a continuous wire, suddenly if you make a kink in it, that's you say wire is broken, and that kind of broken extremals. And we also look at corner conditions. Basically those broken extremal points are corners, physically a corner in the curves. We will discuss that, and that also can be extended to surfaces, that is 1 dimension, 2 dimensions and 3 dimensions. It has important implications in applying variational methods to mechanics. We will consider some of those examples as well. So, let us begin with this concept of a general variation and look at outline of this part of the lecture. So, we will consider variable end conditions, that is what leads to the concept of general variation, and that leads to what we call transversality conditions and also this corner conditions named after Wierstrass and Erdmann. Actually there will be another n here. Okay. What we will learn here is how to deal with variable end conditions and how we can take this general variation, which is more than the Gattu variation that we have studied so far, and we will see how broken extremal looks like through examples. So, we will look at some examples to look at this broken extremal. In fact, one example that we would take would be the very first problem that we had discussed, which is the Fermat effect refraction. Okay. We can call it Fermat's observation, we can even call Fermat effect, because he is the first one to explain refraction of light, saying that light takes the minimum time path and not minimum distance path. Okay. So, that is what is our agenda for this part of the lecture. Okay. So, as a motivation for this, let us consider the famous problem in calculus of variations, which is under the effect of gravity. If I have point A and point B, we say if I were to connect it with a curve and make a slide out of it, if I leave a ball here and that ball will fall under the effect of gravity, it should take the minimum time. That is what we call Brachistochrone problem, minimum time problem. That is a famous problem. This famous problem is solved more generally, and that is actually general variation that we need to discuss. Now, what we say is that, let us say that this point B is not there. Okay. Instead, what we say is that this point can lie anywhere on this curve. Okay. We can take some coordinate system, let us say x and y. Okay. Let us take a curve called phi x, okay, that is this. Now, we say we have a ball as it is shown over there, and say that that ball has to come to some point on this. We do not care which one. Okay. You just come and touch this thing under the effect of gravity starting from this point A, right. There are many curves, right. So, we can go there, we can go here, we can go there. So, there are lots and lots of possibilities, right, under the effect of gravity. You make slides in each of the cases. We either string this ball onto the wires, you can just constrain to move there, or we can make a slide so that it goes and goes there. Which one of these will the ball take? Rather, which curve, we can say which curve, if I say this is y of x, right, which curve will minimize the time to go from point A to some point in on f of x on that given curve. This is our given curve. That is the modification we do. What is the consequence of this? Consequence is that when you start, let us say this is our x axis, if I do this, I say this is x1, right, and what is x2? We do not know, it could be this, it could be that, it could be this, it is variable, right. Let us say y star is a solution, then this comes x2, but this x2 is variable, meaning that we know x1, but we do not know that, and yet we have to have the integrand with all its glory, first derivative, second derivative, function, many variables and whatever, right. So, or many functions. When you have the functional, we do not know the bound, right. It need not be only the ending thing, it can also be the beginning thing, one of them we do not know, right. So, that is our real thing here. We may not know this, we may not know that, we should be able to, or maybe both of them we do not know, that is also possible. We can make up problems where both of them are not there. Okay. That is a modification of the Brachistochrone problem. That is what is shown on this slide. We specify point A, all right, but B can be anywhere on this curve, and hence we have a variable condition of this x2 not specified. So, this is x2 that we do not know, we have to find it as part of the problem. You can actually see its generality now, right, because we are not just minimizing the functional that we have, but if the functional is an integral, the bounds are not known. Okay. That is the modification of the Brachistochrone problem, okay, where phi 2 as a function is given here, where point B has to lie, right, and this is the time taken, this is the time taken by the B to go from point A to some point on the curve phi 2x, time taken to go under the effect of gravity from A to some point on phi of x. We do not know what B is, that is an unknown, but that is what we will solve today. Okay. And if you wanted to make it even more general, as I said, I can have one function there, let us call that phi 1 of x, again choose coordinate system, this is x axis and y axis is phi 1. We can also have another thing phi 2, okay. Let us say this is phi 2, that means that my integral of the time taken, I would say x1 x2, but I do not know what x1 is, I do not know what x2 is, both are variable because I can start from any point on this, several points, right, many points on this, and end up at any other point. So, now our search space has really gone. So, I can start from there and go here and go there, or start from there and come here, and right. So, possible curves that we have are too many, right. Out of all of those things, we should pick the one that minimizes this t. This is the variable end conditions, general, both end conditions are variable, okay, and that is what we have shown here. So, this phi f, phi 1 x, phi 2 x are given, and we need to find a point A that lies on phi 1 x, point B that lies on phi 2 x, and minimize our time where both the ends are not known. In fact, whether one is known or both are not known does not matter. One is not known, both are not known does not matter once you understand how this type of problems can be solved. Okay. and so our general variation that is needed for the problems which have variable and conditions looks exactly like this. The change is only in the ends. Those are variable ends. We do not know what those are, we have to derive them. Okay. For that we need to do this general variation concept. Along with y, we should arrive at x1 star at x2 star. So, now we need to find, so far it was just a function, we have to find a function which we denote as y star x, but here we also need to find x1 star and x2 star if they are not given. Sometimes one of them may be given, other is not given, but sometimes both may not be known. If both are given, that becomes a normal problem. If one of them or both of them are not given, then we have this concept of general variation. What is general variation we talk about? Let us discuss that first. So, let us say we take our x axis and this is our y axis, the function that we are trying to determine, right. So, let us actually call this x1 and x2. So, let me actually draw a curve which might be, let us say from here till here in some form, okay. That is what we call y of x, which may be the solution y star also, okay. Now, in order to check if that is, let us call this y star, which is the solution that minimizes a functional, right. But now, in order to check whether it is actually the minimum, we have always been doing perturbation, right. That perturbation is this y star, we need to perturb it so that it is different. Now, since x1 and x2 ends are also not known, we have to perturb them also. Let us say this becomes x1 plus delta x1 and x2 becomes x2 plus delta x2. So, delta x1 and delta x2, these are the perturbations in perturbations 2, let us call it, they are not perturbations in, they are perturbations given to the ends which we do not know, that is why we need to do. See, whenever we say local, right from the beginning of this course we have been saying, if somebody gives you an answer and says this is the minimizing quantity, a number or a function, we need to perturb and see locally it actually gives the least value of the objective function with or without constraints. So, here also when we say that this is the minimum, it is not enough to perturb y. So, y star that we have, right, we can give delta y for it perturbation, right, but we are not satisfied with that here because end conditions are also not known. So, we have to perturb the end. So, delta x1, x2 are those perturbations. That means that I need to define a new function, let us say from here that one and from here somewhere we have to do this. The new function has to go from here to here, something like that. Okay. So, from the red curve to blue curve, this is the perturbed one, this is y star that we have plus delta y, right. Notice that the domain of delta y has changed, right. This is the new domain. The old domain, if you see, the old domain is from here to only here, x1 to x2, but now it is from x1 plus delta x1 to x2 plus delta x2. That is what we should do and see what happens. Okay. It may look very complex at first sight, but once you understand what this general variation that we talk about, right, once you understand, the answer is actually quite simple. It is a profound concept, but it is a very simple concept, right. We are perturbing the domain as well as the function, and that is what is shown here. And we have a very fancy name to it called non-contemporaneous variation. Okay. What that means is that this concept was developed mostly for dynamics problems where the independent variable x was actually time t, right. When you are saying that I want to do from t1 to t2 your function defined, now we have t1 plus delta t1, t2 plus delta t2, right. Because of that this non-contemporary, that is we are not doing the same time, right. It is not contemporary, it is non-contemporary, that is what this is, general non-contemporaneous variation. So, we have our y star that is given and then we have the perturbed one with this y star plus hx in our terminology or delta y both. So, h is delta y, we have been interchanging that, basically that is the variation. Here we call it general variation, this is variation, we call it general variation because of changing the domain also. So, we take this delta j to see after perturbation the functional value increases or decreases, or to first order it should be equal to 0, that is our criterion. To first order the function should not change it and then we will say whether it is low minimum or a maximum. So, we do from delta x1 plus x1 plus delta x1 to x2 plus delta x2, subtract from it our usual functional over the original domain. Okay. And that is what we have taken, but we rearrange a little bit so that our limits are x1 to x2 for the functional with h and without h. If you look at this integrand, okay, let me change the color of the ink. Okay. If we look at this over there and this over here, both have the same domain, but we know that originally this one, that is integrand that depends on the function and the perturbation, okay. That one we have, it was from delta x1 plus delta x1 to x2 plus delta x2, that is from here to here. So, we need to subtract and add so that it goes from x1 to x2. Okay. So, this part is subtracted because this is included when you go from x1, whereas it is starting from x1 to delta x1. So, x1 to x1 delta x1 is subtracted and x2 delta x2 was there here, okay. Originally we have this for further, that has to be explicitly added so that everything is the same. Now is the critical thing, very simple but very important one. If you look at these limits, it is going from x1 to x1 plus delta x1, that means that it is going over a very small distance delta x1. Because small distance delta x1, we can simply write that portion as f value at x1 times delta x1. Okay. So, this particular integral that I am underlining is nothing but this little term here, because their integrand is not going to change much because we are going to make delta x1 or perturbation delta x1 delta x2 as small as possible, that becomes f evaluated at that point x1 times that, and likewise the second one, let me take a different color and say this one, right, that basically amounts to this term, because in that little range from x2 to x2 plus delta x2 does not change, it is enough to take f evaluated at that point times delta x2. Other two things, the first and second term, that is what are in this line, they are as it is, that is usually what we had earlier. Okay. That is the difference. One other difference, if you see what we have here is the h that we are writing. Okay. I just said in the earlier slide that h is delta y, but here there is a small difference. Okay. That difference is what we will find out now, right. If you see what is perturbation h versus what is perturbation delta y. Okay. Let us understand delta y, if I say at the left end delta y1, it is from a point that is here to the new point that is there. Okay. That is delta y1, but what is actually h, that is h will be the between the two functions. If I take any point here, that will be h, okay. That will be h here, whereas delta is the corresponding points, the contemporaneous, we can call it that way, because this points actually correspond to this point, but at the end, right, again this point okay, is corresponding to this point. Let me put arrows. So, this point and this point we are comparing, that is delta y1, whereas at the same point if I take and same point on the curve, that is h, perturbation of the function, where a delta y is actual variation including the domain condition there. Okay. So, we have now delta y and delta y2, and those relationships are given here by extending the curve. If you see, we do not have anything here. If I want to know what is h here at this point x1, what is h, we do not have a point there because red curve does not come. So, we have extend the red curve like this, right. I am over blue, I am writing this extended curve with the same slope, and that is what is given here, y1 prime times delta x1, similarly y2 prime delta x2, because we are extending that a little bit over there like that, because we do not have, if you want to say what is h there, and what is delta y1 that we have from here to here, it is h1 that is from here to here, that is h1 plus that part which is y1 prime to delta x1. Similarly, delta y2 is h2 plus y2 prime delta x2, and that is what we will use when we try to solve this one. Now, we have h1 h2, we replace that in terms of delta y1 and delta y2. Okay. If we do that, what we end up getting is our, and then we have to do the usual thing, that is Gattu variation equivalent here when we have this and this. Okay. F y star y prime star, we have y sub y h y prime h prime. Okay. And in order to get rid of this h prime, we do integration by parts, that gives us the differential equation part of it. Integration by parts will give you d by dx, that usual thing, and we also get the boundary condition. Okay. And that is what is shown here with the boundary condition put at x2 and x1. Now, what we do is for this h, we replace in terms of our delta y and y prime and so forth, right. If we substitute there, and also remember that delta j that should be equal to 0 had these terms also. Okay. Now, overall what we get in delta j, substitute everything, boundary conditions come, these are the usual boundary conditions, these are special boundary conditions that we got because of the perturbation of the domain itself, that when we substitute what we had for delta y1 and delta y2 in terms of h1 h2, what we end up will be this integral, to which we can apply fundamental lemma of calculus of variations, because h is arbitrary and hence we get our Lagrange equation as it is. But now we get perturbation in delta y and perturbation in delta x, okay, because additional one comes y prime because of these terms, right. This, notice that now we have perturbation in delta y, function and domain independently, we get boundary conditions for both, okay, and that is what we have. We get in the function perturbation, this is domain perturbation. If domain is not perturbed, it is fixed, let us say, that is endpoints are given, x1 x2 are given, then this will be 0, the condition satisfied. So, that is why it is called general. It is valid for this and the specific case we discussed so far in calculus variations, where ends are given. When ends are given, delta x is 0, and so it is satisfied. If it is not given, what will be 0 is that f minus f prime times y prime is equal to 0. Okay. We can actually get it out from the general thing, we can get the specific one that we have discussed so far, and for that boundary condition is exactly what is shown here, dou f by dou y prime, which is that, times delta y equal to 0, y is specified, that is 0, y is not specified, that is 0. Okay. That remains the same. Okay. Now, so far general variation, we said x1 x2 is just not known, whereas now we are saying they have to lie on some curves, phi 1 on this side, phi 1 on that side, phi 2 on this side. What does that mean? That means that when you take this into account and observe these relations, right, delta y1 now cannot be anything, because it has to satisfy between delta x1 and delta y1 we have the derivative of phi 1, and then delta y2 and delta x2 we have derivative of phi 2 unit substitutes. Earlier this boundary condition were separate. Now we can replace delta y in terms of that, and for both ends, then we get separately for x1 and x2. See that 1 and 2 together. Let me change the color of the ink. Yeah, 1 and 2 together become, of course these were from x1 to x2, right. Now we have written one condition, another condition x1 x2, because we have two different curves. So here the curve involved was phi 1x, right. Here the curve involved is phi 2x. Okay. 1 and 2 actually were at x1 and x2, there were actually 4 conditions, 2 conditions here, 2 conditions here, that becomes actually only 2 conditions overall. Okay. Here 2 plus 2, total 4 conditions are there, x1 x2 this condition, x1 x2 the other condition, 4, but now we have only 2, because we have found a relation between delta y and delta x, because once I am here, if I have to be here, when I move delta x1 I also have to move delta y2. So those are constrained. Okay. Let me draw a little bigger, maybe somewhere here. If I move from there to here, if I move so much, I have to necessarily move delta y. Okay. That is what are these relations. Okay. And these are called transversality conditions, right. Why the name? We will examine, all right. So, but the conditions look like that. When the end is fixed, then delta x is 0, then this must be 0, this can be need not be 0. When end is not fixed, then that must be 0. Those are the transversality conditions. We understand what those are. Okay. So, transversality actually comes in the following way. If we take a problem, our integrand is of a particular form, because historically, and that is how it got developed. The integrand here is of this form, f of y, and then y prime has a specific form of square root of 1 plus y prime square. As you see this, you recognize that is basically ds, or the arc length on a curve, that is square root of 1 plus y prime square, dx square plus dy square root. When you take dx out, that gives you 1 plus y prime square, and the f prime f of y can be anything. If it is that form, now we substitute into the transverse condition that we derived in the last slide. If you substitute for f y prime, because that is what we will have, then we get f, which is simply f times square root of 1 plus y prime square, and here we have dou f by dou y prime, that gives you this. If you simplify as it is done here, you would end up seeing this y prime phi prime is equal to minus 1. What does that mean? We are looking at phi of x curve and then y of x curve, their derivatives at that end point are, their product of the derivatives is equal to minus 1. That is true of the curves which are perpendicular to each other. So, if I have one curve, let us say there is another curve, let me take a different color for it. Let us say I have another curve like this, at this point, okay, it is 90-degree slope, okay, they are orthogonal, two curves at that point, right. How do you say? We have to draw a tangent to this, and let me draw the tangent to this in its color, okay, tangent to here, between those two we have 90 degrees. So, orthogonal, that is the thing, that is they are transversal, right, they are transverse to each other, that is where the name transversality comes in, okay, that is transversality, all right. That is only for special thing, but the name has stuck, as it happens in any field. Somebody calls it something, that names get stuck, and here even when the integrand is not of this special form, we still call them transversality conditions, okay. And for Brachistochrone, if I take phi 1 x and phi 2 x, then what you would know is that if I choose the point A, then it has to be perpendicular to the curve there, that should be 90 degrees, and likewise at this point also it should be 90 degrees, whatever point you take, go there. Okay. Transversality here exactly matches because you will have y prime in the same way here. Okay. And let us look at an example. It is an example that requires little bit more work for us to apply what we have discussed, that is a general variation. Consider a beam from mechanics, it is our normal beam, we have fixed one end, right, that is no problem, like cantilever connection. Right side we are saying that there is a function phi 2 x, here I am showing like a line, but it can be a general curve also like that, phi 2 x, and this right end of the beam can be anywhere. This is a physical problem, right, you have put something and you have propped on the surface, as you apply the load it is going to slide on it, right. So, what is x 2 for this beam we do not know, because if the beam bends like this, that is from here to here only, right. On the other hand, if the beam, if I use a different color, on the other hand if the beam bends let us say like that, then the domain is from there to here. So, variable and condition. So, we do not know that end point, we do not know that. But the difference here is that we have now y double prime. We discussed in the previous slides, when the integrand has y prime we discussed, now we will discuss what happens if it is y double prime, what happens when it is y triple prime and so forth, okay, which is what we will do in the next part of the lecture. Thank you.